Okay, so yeah, sorry for the delay. Let's begin. So today's title is Heine's method, and today we will get to in the exercises at least more than 20 identities of entries of Ramanujan. So this method today is quite easy. It's one of the early methods, but we get a lot of stuff out of it. So let me begin sharing my screen. Okay, can you see the screen? So so this is the target identity. It's a transformation formula and it's quite symmetric. And this is from Ramanujan's notebooks. It's entry 6. So just recall. Let me begin from here. So recall, this is what we did last time in lecture 2. We did the q-binomial theorem. And this can be written like this. Q sub k, q, q, k going from 0 to infinity, a raised per k. So this is a. This is qa, and this is equal to bq infinity over aq infinity. A is less than 1 for the series to converge, and q is less than 1 for these products to converge. So this is the q-binomial theorem. And if you recall, this chap, bq infinity, is the product as k goes from 0 to infinity, 1 minus bq to the k. We had bq sub k. This was 1 minus bq to the j going from 0 to k minus 1. So these are q rising factorials. So these are all the terms over here, and this series can be summed. That's the point. So we will use. So instead of this series, we consider slightly more complicated. Consider this sum. K going from 0 to infinity, and in place of so b by a is there, and then add a parameter here, and q, and add a parameter here. So and leave a raised per k. So these two items are added, and we are using this notation that a1 through a2 up till an sub k. This is just a1, sorry, q over here, a1 qk, a2 qk, and so on. an qk. So some compressed notation we are using, and we've just added one parameter. That's all. Right. So and if you recall, aqk can be written as aq infinity divided by aq to the kq infinity. So what are we saying? We are saying just first k terms here of this guy, and after the kth term, these cancel. So this is what we will use. So this chap S, let's say, is equal to, so S is equal to, so we just apply this on these new guys, C sub qk and D sub qk, and we will get CQ infinity over DQ infinity, summation k going from 0 to infinity, B over A qk, and then the bottom one will give you this. Then you have QQ infinity from here, from this guy, and the top one will give you CQK, Q infinity. And there's a raised per k. So now this whole thing is repeated, CQ infinity, DQ infinity. This part stays where it is. And this product, we can again apply the binomial theorem. So we apply the binomial theorem. Let me use M. Right. So this is this will come out to, in the numerator you have D over CQM. In the denominator you have QQM, and this part comes in the CQ to the K, CQ to the KM. Maybe I should write bigger, smaller. CQ to the KM. Right, so this is using Q binomial. And now we interchange the sums. So CQ infinity over DQ infinity. D over CQM, QQM. This part, C raised per M, comes outside. Then the stuff about K. And you have P by A, QK, QQK. And this Q raised per, so A Q raised per M raised per K. So these two guys, this guy comes here. Right, and now again, we can use Q binomial theorem on this guy, the last chap. So this is as it is. So if we use Q binomial theorem here, we will get B over A times AQ to the M, Q infinity, and AQ to the M, Q infinity. And again, we use the same idea here and multiply and divide. So this gets cancelled. B over A and A gets cancelled. I should do a smaller pen. And I get CQ infinity, DQ infinity. And this is BQM. So if we divide by BQ infinity and multiply by BQ infinity, so you'll get BQ infinity on top. Wow, I want to green color. So this chap will give you BQ infinity here, and so you multiply and divide by AQ infinity. When I write the whole thing, you'll know what's happening. M equal to 0 to infinity, D over C QM over QQM, C raised per M. And so you'll get at the bottom BQM, and at the top, is it right? Yeah, AQ. Right. So now let me make it smaller. What we've got is S is equal to this sum is equal to this two products and then this another sum. So this is called Heine's transform. This is called Heine's transform. Right. So so what are we? I'll just rewrite it. So when there are yeah, maybe this pen. When there are several parameters, we use a notation. We use the RFS notation. We use some notation. The following notation to save some space. So let me define it. And this is basic hypergeometric series. So let A1 to AR and V1 to VS be parameters, some parameters, which means could mean anything. So could be complex numbers or indeterminates too, if you wish, but typically complex numbers. The basic hypergeometric series with R numerator parameters and S denominator parameters. With base, so the basic comes from base. Q is defined as, so we write R phi S and we put A1 on the numerator, AR, B1 in the denominator, then put a Q and Z. It's a power series variable. So this is defined as summation K going from 0 to infinity, A1, comma, AR, QK, B1 through BS, QK, and then there is a -1 raised per K and Q raised per K choose 2, and the whole thing, this whole thing raised to the power 1 plus R minus S and Z raised per K. Now, so this is the product of Q rising factorials. Notice an extra Q here. So there are S denominator parameters and Q here. This term, when R plus 1 is equal to S, when S is equal to R plus 1, this becomes 0. So this whole term disappears. This is a power series. So this is called the argument. I can put some colors. This is called the argument. And this one is equal to 1 if r plus 1 is equal to s. So typically we have one extra parameter here, and this is the hidden parameter, so they are actually matching over here. And as an exercise, using the ratio test, you can prove that when r equal to s plus 1, then it converges, the series converges absolutely for absolute value of z less than 1. So provided, of course, absolute value of q is always less than 1 here, and it converges uniformly in z less than equal to, say, 1 minus delta for any delta bigger than 0, delta small. So this is from the standard power series theory. If it converges absolutely here, so the radius of convergence is 1, so its convergence is uniform. If you just take a closed disk. Okay. So in this notation, using this notation, we write this entry as the result we proved as. So this is entry 3.16.6. It's called Heine's transformation. Formula. And we can write it like this. So 2 phi 1, numerator parameters are C, B by A, B, Q, and A. And this is equal to B, C, Q infinity over A, D, Q infinity, 2 phi 1, A, A, D by C, and B in the denominator, Q, and C. And here, absolute value of, so let absolute value of A and absolute value of C be less than 1. Right, so it's quite symmetric. And this is Heine's transformation formula. And this technique is called Heine's method. That so the technique is that you you take two of these things and you expand them and you interchange the sum, and then you again apply the q-binomial theorem. So when you expand, you again apply q-binomial theorem. So it's remarkable that this technique is so productive, and we get this formula, which is called Heine's transformation form. Okay, so well, now this is it. I mean, this technique is quite useful, and let me make some notes. Remarks. So if you put C equal to D, so you can see over here, if you put C equal to D, this term becomes equal to 1. So 1 sub K is 0 unless K is 0. So this one becomes, so you get 2 phi 1 of 1 here and something else. This is just simply 1. So when that happens, when C equal to D, then this becomes equal to D. You just get B over A, and you get this cancels. There's the same numerator and denominator parameters, so you just get what is the q binomial theorem. So we get q binomial, which is 1 phi 0 and B by A, nothing in the denominator, and this is equal to B q infinity over a q infinity. So this is just the q binomial theorem. Oops. Right. So this side becomes 1. Now suppose I put c equal to d. Instead of c equal to d, I made c equal to b over a. So the second thing which we can do is instead we can take, let b by a be equal to d. So d is b by a. Then what happens? So then the left hand side becomes a q binomial. Right, so then left-hand side becomes 1 phi 0. So these two terms cancel. And we get 1 phi 0, c with a numerator parameter and a. So that we know how to do. So the left-hand side becomes a c q infinity over a q infinity. Right, and the right-hand side, so this means that the right-hand side, so you get a c q infinity over a q infinity is equal to this guy. So into a q infinity, and d is b by a q infinity. So I'm just bringing this on this side, and then divided by b and c q infinity is equal to 2 phi 1. This is a. D by c is b by ac. B by ac, and in the denominator is just b, q, and this is c. And again, this a cancels with this a. So you get AC comma b by a, AC comma b by a, and BC is equal to 2 phi 1. And what we do is we just to make the product side more symmetric, we replace a by 1 over a and c by ABC. So this is in Ramanujan's notation. So a goes to 1 over a, c goes to ABC, so the top becomes BC. And a goes to 1 over a, so it becomes AB, q infinity. Then b is b, c is c. No, c is ABC. Sub infinity, and this is equal to 2 phi 1 over a. So a goes to 1 over a, c goes to a over b, it becomes 1 over c, b, q, ABC. Right, so I mean, the way Ramanujan wrote it was by interchanging a and b, and so interchange to get. Now we get another entry of Ramanujan. This is 3.16.4, and this says that AB, AC, Q infinity, and A and ABC, Q infinity is equal to 2 phi 1, 1 over B, 1 over C, A, Q, ABC. So this is an entry, and this is for, again, ABC has to be less than 1 and Q has to be less than 1 for this to make sense. And this is called a Q analog of Gauss's sum. So when we learn how to take limits, we will see how this can be written as it's a generalization of result of Gauss. So I just want to remark that this is how Ramanujan wrote things. So Ramanujan, so ASCII has remarked that Ramanujan wrote that Ramanujan wrote his results to highlight the symmetries of the product side. And usually we write it as a sum equal to some product. So I will show you how we usually write this thing. But this is a result of Ramanujan, which follows immediately, and it generalizes a result of Gauss. So let me see how to write it usually. This is written as follows. So you write it as 2 phi 1, and we write A, B, C, Q, and C over AB. And this is C over A, C over B, Q infinity, C, C over AB, Q infinity. So this is as it is. So this, let me write it as 1. This is as written in Gasper-Riemann. So the other reference, which is kind of like the Bible in this area, is Gasper and Riemann, basic hypergeometric series. And this is equation 1.5.1 in this book. So this was in 1990, and then a second edition came out, I'm not sure when. I'll give the reference in the notes. So this is how it's usually written. It's a Q analog of, this is a Q analog of a famous result of Gauss. So Heine wrote a paper to generalize Gauss's paper about 100 years after Gauss, and we will learn this. We will see this when we learn how to take limits. So one more idea we need to take. So we had one limit which followed from q-binomial theorem. There's one more which we need to learn. After that, we'll be able to take. We will see what this Q analog. What is it a Q analog of? Okay, so corollary. I have a coffee, so I should keep drinking it. So a finite form of identity 1, you take Q, one of the numerator parameters is Q raised to minus n. So what happens is that you'll get a terminating sum. So you'll get 2 phi 1, Q raised to minus n, B, C, Q, and then CQN over B. This is equal to C over B, Q sub n, and CQN. So this is now a finite sum. So it's K going from 0 to n. This is equal to K going from 0 to n of Q raised to minus n B Q K over C and then Q Q K, and then CQN over B raised to K. So this is a finite sum because this item right here becomes 0 when K is bigger than n. So this we did as an exercise earlier, that this terminates the series. So now you don't need any thing. And these follow straight from what we did. So if B is Q to the N, then this will be C infinity, and this will be CQ to the N infinity, and then that will become CQ sub N. And similarly for the second one. Right, so now there is another finite form, and this is an exercise. I'll indicate how to do it, but you can write it slightly differently. And this is just Q here, and you'll get C by B Qn over CQn, and then there's a B raised for n. This is the other finite form. So, so this is the other finite form. So this is an exercise. So A implies B is obtained by reversing the sum, which means you'll write something like this as n minus k. So you take so you write it from the other way around, right? So this is how you do it, and then you have to simplify, and you simplify this and relabel to get the answer, to get this identity. So that's how this is how to do the exercise. Another possibility is also you may invert base. Now, when it's a finite sum, then Q less than 1 is not necessary. So you can replace Q by Q inverse. So take P and then write the sum again, and then you'll get the same thing. So I'll add an exercise about inverting the base, and this will follow. And the other note again, which I will not explain, but it is these are Q analogs of very popular identities from high school. So these are Q analogs of what are called q-Vandermonde identities. Convolution. And this q-Vandermonde, this guy was 1303, a very old person. So this is 1303, and this is some 1700s. Vandermonde, who discovered this identity. I'll tell you the identity because I mean you've seen this. So this identity follows from this kind of technique. So this is binomial theorem, and if you write this as a summation n choose k, m choose k, x to the k, and this one as n choose k, x to the k, both on k, and this one you will write it as m plus n choose k, x to the k. And if you compare coefficients, then this will be m choose k or L, m choose k minus L. So the sum will be on k. K going from, no, sum will be on L. To the smaller of these two. So one is m, one is n. So you're multiplying these two and then comparing coefficients of x to the k on both sides. Then you will get m plus n choose k. So from here to here, you compare coefficients of x to the k. So this is called q-Vandermonde, and if you write it in hypergeometric form, you will get this identity. So these are actually very classic binomial identities which are very useful. Right. So the thing is that these are the results which I've just mentioned are from the chapter 16. So this was the notebook, Ramanujan's notebook, which was before he went to England. And then this same idea and lots of such identities show up in the lost notebook. So this is in fact the page 4 of the lost notebook. There is an identity. So here is a formula from Ramanujan's lost notebook. So if you recall, Lost Notebook was another 5 volumes by Andrews and Berndt. And here I'm writing the entry, so this is L denoting lost notebook. And then this is the volume number. And then this is the equation number of the entry number over there. And this is, let me write it down, Q infinity, CQ q square infinity minus BQ q infinity and dq square q square infinity sum. This is as Ramanujan wrote it. J equal to 0 to infinity. I mean, he used some other numbers maybe. BQ over K, A, Q, J, BQ square, Q square J divided by QQJ, CQ, Q square J, AQ to the J. And this sum is equal to K going from 0 to infinity, CQ over D, Q square K, Q square K, and AQ, Q2K, and minus BQ, Q2K plus 1, and DQ square to the K. See. Right. So this is now this is very similar to what we had. The only difference is that there are some q square here. Base is q square in 2 of the terms, right? Q square here. And here, there is a sub 2k and sub 2k, right? And otherwise, there are 4 products and two on top, 1 at the bottom with a q. And here there's a q square, but 2 on top, 1 at the bottom. So if you look at, where are we? If you look at this one, Heine's transform, it's very similar, right? So it's again 2 products, 2 at the top, 1 at the bottom, and then 2 at the top, 1 at the bottom, all in base q. And here, however, it is base q square and base q. That's all. That's the only difference. And the proof is very similar to the what we did earlier. So let me quickly indicate the proof, and then I won't give all the details, but what we will do is we will take this guy right here and then expand this. So we will take these 2 guys. So in the proof, we'll take these 2 guys and expand it using Heine's method. So we'll expand it using this thing. So left-hand side, let me write it here. Yeah, so left-hand side is equal to, let me just bring this here. Where are we? Just copy it and paste it here. Oops. What happened? Oh, here you go. There you go. So the left-hand side, oops. The left-hand side. So we just expand this guy, dq square infinity, and this will cancel this chap. So it's just aq infinity over minus bq infinity. This will cancel, and we'll get some j going from 0 to infinity minus bq over a q sub j and qj. And then this chap will be written as m going from 0 to infinity. So there is a, well, maybe I'll add this step. So we have dq 2 plus 2j q square infinity and cq 1 plus 2j q square infinity and aq to the j. Right? So this is again using q-binomial theorem. This is q-binomial theorem. Same technique as we did earlier. And we have aq q infinity over minus bq q infinity. And then I have two sums, minus bq over a q in q sub j, q sub j, and then this is a q to the j here, and m going from 0 to infinity. So again, now this over this, so it's c, have I got it right? cq over d should get. Or c over dq, one of those two. Let's see now. Oh, this is, there's something I did wrong. And that's why it's causing this problem. Okay, here you go. So sorry about this. Let's go back. I think I copied this wrong. This was j plus 1 over here. And this is 2k plus 1. This is fine. So this is j plus 1. And yeah, so this is actually 3 plus. This should be 3 plus 2j. aq to the j. And now we'll get the correct value. So now we'll get cq over d, q square m, and q square m, and dq 2 plus 2j raised to the power m. So this 2j comes because the base is now q square. So everywhere this guy is sort of double of the previous chap. And now we get again aq q infinity minus bq q infinity, and we interchange the sum as usual. CQ over D, Q square M, Q square M, DQ square. This was AQ to the J here. DQ square M, summation, J going from 0 to infinity, minus BQ over A, QJ, QQJ. And now this J has to be there. So it's AQ 1 plus 2J, 1 plus 2M raised per J. Right. So AQ to the J, A to the J, Q to the J plus 2MJ. And this DQ square M comes here. So this chap, again, we use Q binomial. So this is equal to minus BQ over A times this number, AQ1 plus 2M, Q sub infinity, and AQ1 plus 2M sub infinity, Q sub infinity. And rest is all the same. And then if you write this in terms of AQ sub infinity, etc., you will find that you'll get AQ sub infinity in the bottom and whatever. So this, I will put a equal to sign and say this is equal to M going from 0 to infinity, CQ over D, Q square M, Q square M, DQ square to the M, and these guys will lead to AQ, Q2M, and this A cancels right here, minus BQ square minus, no, just BQ, Q 2M plus 1. Right, and that gives you the right answer. So this finishes it. So, so the point is that Ramanujan used this, and in the lost notebook, there are something like 14 or so special cases of this, which I will include in exercises. So 14 plus this one, 15 plus 2 more we did, 17 identities we've already done. And there may be more. So I would say approximately 20 identities now we have got, more than 20 we have got out of, I don't know, 4,500, but still. So now it's moving faster now. Every technique will give rise to more and more identities. And as we study more, the same techniques are applied repeatedly. So that's the point. I mean, we are going to sort of reduce the thing. So again, the idea is very simple. You expand using binomial theorem. You interchange sums. Again, the inner sum happens to be summable by binomial theorem. And then you get the answer. And this is what Andrews and Berndt call the Heine's method. And this gives a lot of special identities, and I'll include some in the exercises so that you know what they are. So here's one example from Ramanujan before we close. And in the lost notebook, this is what it looks like. J going from 0 to infinity, minus 1 raised per J, Q raised per J square plus J, divided by Q square J, 1 minus Q raised per J plus 1. This is equal to Q square infinity, Q square infinity. So I mean, this doesn't have any parameters. When you don't have any parameters, then you don't know which place to go. So typically, this is Ramanujan's trick. He would find general results through a somewhat easy method. Then he would specialize them in some weird ways and simple ways for some reason, and then present those, and everybody will say, "Oh, this is genius. I mean, this is great. How did he get that?" So this has got less degrees of freedom, less manipulations you can do to prove it. And of course, he calculated stuff on his slate. And as you see, the methods so far are not very far from what you don't require to be an inventive genius to do that. But let me say that later on, we will find some reasons why Ramanujan took some certain types of special cases. So, but the moral of the story is to understand your own result. Sometimes we don't spend enough time to understand, to play around with our own result, and that leads, and this Ramanujan used to do. So the moral, this is I would say one of the morals of studying Ramanujan's work, that he found lots and lots of special cases, and they look very mysterious. But then he tried. So you find some result, but then you need to see what it's good for, and you try various special cases. All right. So yeah, that's it. And the next lecture. So the next lecture will be on a slight variation of Heine's method to get more transformations. And then we will look at maybe some infinite product theory, so that we understand how to take limits. But next lecture will be on maybe in 2 weeks or 3 weeks on some slight variation and exercises. I will take a bit of time to make the exercises, but there will be around there'll be around 20 such things. There'll be many entries from now. So the whole from now on, there'll be each technique should give many things. Okay, thank you very much. Any questions? Yes, Pramod, please go ahead.
Thank you for the talk, sir. Sir, in the exercise following the definition of basic hypergeometric series,
Yeah.
Is the condition same as that in the definition of the hypergeometric series, or both of them different?
So yeah, hypergeometric series also have the same thing pretty much. So when you have hypergeometric series, there's no q, and you get absolute value of z less than 1. That also converges by the ratio test. So the answer is the same, except there's an additional power of q, but that goes to 0 when q raised power k goes to 0 as k goes to infinity. So yeah, I mean, in fact, it's even easier. It converges much faster.
Okay. And is the relation between R and S the same in both the definition and the exercise?
No, yeah. So
could it be the same?
in the exercise, I'm saying no. In the definition, R and S could be anything. All I'm saying is that when when R plus 1 is S, then this term vanishes. So this is an additional term, which we'll find out there's a reason for this term. In certain limiting condition, this comes out. So there's a reason. The most natural series are R plus 1 phi R. So R is S plus 1.
Right.
So that's the most natural thing which comes up all the time. In fact, they're balanced because you have S here and there's one additional hidden parameter here. So they're the same, then they're the same. Yeah.
Okay.
R
is S plus 1.
Yeah.
Thank you.
Sure. Any other questions, queries?